Welcome back. Hopefully your tutorial went well and you have the solutions in front of you to cross-check with these answers. Let's dive straight into the first one, which is a typical design problem where we are told that a component is 12 millimeters in diameter and it's going to be subjected to a load of 9.43 kilonewtons and the extension mustn't exceed 0.06 millimeters. They also tell you Young's modulus for the material at a typical value for steel of around 200 gigapascals. Okay, first thing we've got to find how long the component must be. Now remember, if the component were longer, it would stretch more. Like a piece of elastic band, a long piece of elastic band will extend more than a short piece of elastic band under the same conditions. And in the same way, our piece of steel had better be 149.7 millimeters long so as to extend only 0.06 millimeters, given that it is 12 millimeter diameter and the load is that much. And of course the formula we use is our E equals PL over EA, which after all came from E being stress over strain. Okay, so now we go on to the part B, where we see that the design now said that 149 was too long. We have to have 104 millimeters only. Perhaps there's a space constraint in your design, we don't know. So the solution to that would be to change the only other value that we're allowed to change, which is the diameter. And if we think about it, if we were to reduce the diameter, a shorter specimen would still be able to stretch as much as the longer specimen, provided you make it of a lesser diameter. Okay, how would we reduce the diameter? Well, we could turn it down in a lathe. And if we now make length the unknown in that very same formula and we keep everything else the same, correction, not the length, we're going to solve for the diameter. Sorry, the length is now set at 104. Remember they told us that over here. Okay, so the length set at 104, and we find that a 10 millimeter diameter would now yield the same extension. Okay, so let's compare. The diameter is now 10. And in the beginning it was 12, so we have to take off 2 millimeter diameter in the lathe. Right, straight into the second one. And we have the typical results from a tensile test. You can read through them over there. But of interest in the first one, which wants to know the Young's modulus of the steel, it's important to find the values that are applicable to the straight line portion of the graph. Okay, so if we go in and we have a look, we've got here we go. At the proportional limit, the load was 25 kilonewtons. Now remember, proportional limit is at the end of the straight line portion. So if we use that as our load, knowing that we are indeed within the straight line portion of the graph, and we find the applicable other values to go with it, 25 kilonewtons load, length of specimen, the gauge length was 50 millimeters, and down here we have the extension, which was given, and of course the cross-sectional area at a 12 millimeter diameter. We can use pi upon 4 times 0.012 squared as the area. And we solve for Young's modulus, and we come out with a value that looks reasonable for steel, around about 200, just over 200 gigapascals. And that looks like a good value for Young's modulus. Second one is the yield stress. Now remember, stress is load over area, so if we can find the yield load, which was given, and we divide it by the area of the specimen, we are in business. That should, of course, say 247.6 megapascals. The units must go over there. Now, interestingly enough, C is the ultimate stress, and here is where you need to be careful. Ultimate stress is ultimate load, that's understandable, divided by original area. Okay, remember that, original area. So it's the same pi over 4 times 12 millimeters squared. And 380.2 megapascals is the stress, the highest stress. Remember, that's what ultimate stress is. The highest stress recorded in this test would have been that. Okay, now we go into elongation. Now, elongation is a comparison of how much the length changed over what the length was initially. Okay, so if we look at the length went up to 62 from 50. So the change was the difference between those two, 62 minus 50. And if we divide it by the original length, we would get a number 0.024. Now 0.24 is in fact 24% when you multiply by 100. So to answer the question fully, they're asking for the percentage elongations. The answer would be 24 units percent. Okay, the last one, the reduction in area, in much the same way, how much did the area change, delta area, change in area, divided by what was the original area. Okay, so the area changed. Let's look at the values. Where do they come from? Here we go. Right at the end, the diameter had necked down to 9.1 millimeters. However, the specimen had started at 12 millimeters. Okay, so the change was final area, original area minus final area. So that would be the change, the difference between those two. And of course, we divide it by the original area. Now the pi upon 4s all cancel, and you can quickly work that out, and you get 0.4249, which, if you wish to express it as a percentage, which is what they asked for, you'd multiply by 100, and there's your 42.49%. Now in the third one, the situation is very typical of what you would encounter in a materials testing lab, where you are given a specimen to test and it must meet certain criteria, certain specifications for the material. Okay, one of which is it must have a tensile strength of at least 620 megapascals. So knowing that stress is load over area, or that load equals stress times area, you know when you do the test that to attain 620 megapascals with its known cross-sectional area, the test had better yield a maximum value of 63.284 kilonewtons or better, and that is the answer to the first one. If we achieve, for example, 60 kilonewtons, we would know that the material had failed the test and would not meet the specifications. So there's the answer for the part A. Yield load is easier to understand. They tell you that the yield stress must be at least 310 megapascals, and once again multiplying it by area, you had better note 31.64 kilonewtons, which as we know would be less than the ultimate load. Okay, in part C, after it's failed, what should the gauge length be? Now it mustn't be more than a prescribed amount, which they've told you. Okay, so let's solve for how long it will be with a 15% elongation. Remember, they said that the material mustn't stretch more than 15%. That is one of the requirements. So if it were to stretch 15% or 0.15, the change in length would go there, and the original length we know already is over there. So we solve for the new length, which comes out to 64.9 millimeters. So at a glance during the test, if you find that you're getting 66 millimeters, you would know that the material had failed the test. Okay, last one is the diameter at fracture we can find by knowing that the reduction in area is given as a specification of 48% or 0.48. So in the same way, change in area goes at the top, over original area goes at the bottom, the pi over 4s all cancel, and we can solve for the final diameter, that would be the diameter of the neck, is 8.22 millimeters. Okay, so that would be the maximum diameter at fracture, 8.22. Now in the fourth one, you are given typical results of a tensile test and a table of the various loads versus the corresponding extensions. And as is typical of a question like this, the first thing to do is to draw the load extension graph, which we'll do in a moment. And then the very first thing you've got to do is find the Young's modulus for the material. Now remember, that applies to the straight line portion of the graph. Okay, but first things first, let's look at how the graph plots. That's a simple matter of drawing it out on a piece of paper and using these loads with appropriate scales. And there we have it. There's our typical straight line portion. There's the yield occurring, and here's maximum load and failure over here. Okay, so that you've hopefully done correctly and as accurately and neatly as possible. And the first thing to find is the Young's modulus for the material. Okay, so remember that that applies to the straight line portion of the graph. And you could simply dive in and take a value that you were sure was on the straight line portion, and you could use E equals PL over EA. But here's a nice experimental technique where we ensure slightly better accuracy by actually spreading it across 2 points that are both definitely on the straight line portion, and looking at the change between those two. So let's have a look how that's done. In this example, I'm using the first and the fourth points, but of course it could be any two others that are most definitely on the straight line. And being an experiment, you would look for values that were as close to the line as possible. Remember, you're going to get slight scatter in a real experiment. So you would pick two points that are nicely on the line. I've taken first and fourth points, and I look at how much the load changed between those two. Turned out to be 26.5 kilonewtons between this one and this one. And also during that time, the extension changed by 0.045 millimeters, taking the two values and finding the difference. And use those in your E equals PL over EA formula. There's the load, which is indeed the change in load, times the gauge length divided by the extension between those 2 points, how much longer the specimen got between those 2 points, and of course the cross-sectional area, and you come out at 200 gigapascals. Okay, so that's the first one done, Young's modulus. Then they ask for the yield stress for the material. Okay, so we've got to go and look up the yield load, which off your graph looks to be about 37 kilonewtons. Hopefully you agree with that. Remember, the definition of yield is when you have a sudden increase in extension with little or no added load. So you've got to find the portion of the graph that is flattest over there. And you are simply taking a reading off your accurately drawn graph, and it looks like about 37 kilonewtons. So in it goes there. There's our original area, and we come out with 209.4 megapascals. Okay, C, the ultimate stress. Remember, that refers to what happened over here at the maximum load point. So we go and find the maximum load, which reads to be 69 kilonewtons off your graph. Put that in, and importantly, use the original area. Okay, and that comes out to 390.5 megapascals. And the reason I said it's important, don't be tempted to use the necked down area. You must use the original area for working out that value of ultimate stress. Ultimate stress is always maximum load divided by original area. Lastly, at fracture, that is where you can use the reduced area, and they told you that the fractured specimen had a diameter of 12.34 millimeters. In other words, that's the diameter of the neck. So that goes in as the area. The fracture load was given, and you find that the load, the stress at fracture is in fact 510 megapascals. Okay, now don't be tempted to use that as the ultimate stress. It's not. That's simply the load at fracture, and slightly academic, not really much use to you in any sort of design environment, the fracture stress, but there it is anyway. Right, let's look at the last one, number 5. Typical results from a tensile test, load versus extension values are given, but they ask for the stress-strain graph. Not a problem, you can work out the corresponding stress and strain for each of those data points by adding 2 columns, this one for stress, this one for strain. Now stress is load over area, we know that, so you would simply take the load, which for the first example is 5 kilonewtons, and you would divide it by the area, which is pi over 4, 0.018 squared, which would give you 19 and a bit megapascals. And you do the same for each of those points. Strain, on the other hand, is change in length over original length. The original length stays at 50 for each of these. So you would take 0.004, divide it by 50, and you would write it in, and you do the same for those. And then you draw a graph of stress versus strain, which interestingly has a very similar shape to our load extension graph, which we've done a number of times, except obviously the values are now stress and strain. Then once that's done, we need to find a few things. Let's see what they are. From your graph, determine Young's modulus. Young's modulus, as we've done a number of times, is applicable to the straight line portion of the graph. So any values along here which are representative of the experiment. Now remember, in a true experiment we get scatter. The lines won't exactly, the points won't be exactly on the straight line. So pick something that is representative, in other words, nicely on the line. I'm taking this value over here. Okay, now that point, rather, has got a stress corresponding to it of 172.9. Here you'll find it was this one over here. And the same point has a strain of 8.4 times 10 to the minus 4. So Young's modulus would be stress over strain, and you come out to 205 and a bit gigapascals as a value for Young's modulus for this material. And then finally, they ask you for the yield stress. Okay, now remember, yield is where we have a sudden increase in extension or strain with little or no increase in load or stress. So that would be this flat portion over here. Find the flat portion, run back over here, and you find about 192 megapascals as being your yield stress. Okay, that brings us to the end of this tutorial.